now it should work. So Kishan, over to you, please.
Okay.
On this slide.
Okay. Okay, thank you. So today I'm going to be talking on a brief introduction to Effectus theory. So my goal of this talk will be to introduce Effectus theory and show why it's important. And doing so, I'll introduce the necessary category theory needed to understand this. So hopefully everyone can follow. So we start with the usual Hilbert space formalism of quantum mechanics, where to each system, we associate a Hilbert space. The states of our system correspond to unit vectors up to global phase. Physical observables or effects of the system correspond to self-adjoint operators on the Hilbert space. The expectation of the observable A in the state psi is given by this product. And lastly, we have the Schrödinger equation, which shows us how the system evolves. One other point that I want to mention is that for the tensor product of two systems, it actually gives us the composite of the two physical systems. Now, this formalism has been generalized. Why would we want to generalize this when the Hilbert space formalism works? This is done due to some researchers having certain objections to the Hilbert space formalism. Namely, von Neumann did not like the fact that states only correspond to unit vectors up to global phase, as well as the fact that he said that the states of the system are a more derived notion. So there were some attempts to generalize the Hilbert space formalism, and we get these three important approaches using C-star algebras, orthomodular lattices, and Jordan algebras. The C-star algebras and Jordan algebras aim to generalize the self-adjoint operators on your Hilbert space, while the orthomodular lattice generalizes the closed linear subspaces of your Hilbert space. The closed linear subspaces, in fact, correspond to projections of your system. So these are three generalizations. However, these three generalizations did not lead to much difference over the Hilbert space formalism, due to the fact that when one wants to study quantum mechanics and impose physical principles on these generalizations, you get back something very close to or exactly the Hilbert space. So more recently, I'd say in the last 20 years, I think, we have the approach of a generalized probabilistic theory. This is also known as an operational probabilistic theory. And here operational denotes measurable effects. Now, what do I mean by measurable effects? Things we can measure experimentally. So this can be like temperature, momentum, etc., as well as more abstract notions that can be verified experimentally, such as Shannon entropy. So formally, what is a generalized probabilistic theory? It's a collection of physical systems we denote by capital letters. To each system, we have a set of states of the system, which we denote here. The set of states of a system, we are able to combine states in certain ways. These are convex combinations. What does this mean? We can take any value p between 0 and 1 and obtain a new state for two given states, omega 1 and omega 2, by taking p times omega 1 plus 1 minus p times omega 2. This is interpreted as prepare the system in state omega 1 with probability p and in state omega 2 with probability 1 minus p. We also have transformations between systems given by maps between systems A to B. And we also require that a transformation from a system A to B also defines a transformation from the states of A to states of B. So what do the effects of our system correspond to? So given a physical system A, the effects on A is given by the functions from the states of A to the interval 0, 1. But these functions must also satisfy this property here. F of this convex combination becomes P F of omega 1 plus 1 minus P F of omega 2. These are sometimes called as affine functions through the interval 0, 1. So for a given effect, an effect of the system A, what is the probability of the effect A when the system is in state omega? We simply apply the function A on omega to obtain a particular value in the interval 0, 1. Furthermore, we required the set of effects to be a probability distribution. So we want the sum of A of omega ranging over all effects to add up to 1. So this notion of a generalized probabilistic theory, or GPT, allows one to formulate a theory of quantum mechanics where to each system we correspond a matrix algebra over the complex numbers. States then correspond to your density operator, Measurements correspond to a set of effects. These are matrices in your matrix algebra such that when you sum them up, they become 1, where this is taken to be the norm of the operators. We also have probability of effects. So what is the probability of effect EI when the system is in state P, or usually denoted rho? It's given by the trace of P multiplied by EI. In this case as well, tensor products do correspond to composite systems as well. And here, transformations correspond to completely positive subunital maps, which where subunital simply means trace non-increasing. So because we were able to take convex combinations of states, the set of states of a system form what we call a convex set. The set of effects now form what we call an effect algebra. What is an effect algebra? It's a set E with a partial operation plus and two constants 0 and 1 with a unary operation, which is denoted by this negation here, such that plus is it's a partial operation, which means we can't add every two elements of E. It's commutative. Next, we require negation to be an involution on E. X plus negation of X is always 1. 0 acts as an identity for your addition. This operation is associative in the following sense. If we have X plus Y in brackets plus Z, it has to be equal to X plus in brackets Y plus Z, where the two operations on the right-hand side must therefore exist. Lastly, we want that if X plus 1 is defined, then X must equal to 0. What are some examples of these effect algebras? We have the interval 0, 1 with our standard addition, where we can't add any two elements in 0, 1 because they might not be less than or equal to 1. And negation just becomes 1 minus X. Two other important examples are Boolean algebras and the effects of a C-star algebra. Now, any effect algebra E becomes a partially ordered set in the following way. For two elements X and Y, we say X is less than equal to Y if there exists a Z such that X plus Z equals Y. So there's a typo here, sorry about that. So why are these effect algebras important? So the example I gave earlier of orthomodular lattices is a generalization of a Boolean algebra where distributivity is dropped. Now, effect algebras generalize orthomodular lattices by making the join a partial operation. So we don't stop here. We want to generalize now a GPT, or generalized probabilistic theory, using category theory. In particular, we saw that the probabilities or scalars were the interval 0, 1, and the states and effects form certain convex set and effect algebra. We want to now formulate this in category theory, where our scalars are some effect algebra, not necessarily the interval 0, 1. So before I get to that, I'm going to introduce a bit of category theory necessary. So firstly, what is a category? It's a collection of objects, denoted objects of C, and a class of morphisms of C. Morphisms you can think of as just arrows between objects, such that if we have an arrow from X to Y and an arrow from Y to Z, they are composable, and we must have one arrow from X to Z denoted by GF here. This composition must be associative. And lastly, for any object X, we must have this identity arrow going from X to itself, such that composing any arrow F with the identity arrow on either side gives us F back. We then have functors between categories. These can be thought of as maps between two categories, where a functor F from a category B to category C formally is defined as a mapping from the objects of B to the objects of C. So for each object B in B, we have an object F of B in C, and we have a mapping from morphisms in B to morphisms in C. So if we have an arrow from X to Y in B, then we have an arrow F of small f from F of X to F of Y in C, such that the following two conditions hold. We want F of identity arrows to be identity arrows, and our functor must preserve composition of arrows in the following sense. If we have G and F being composable arrows, then F of G composed with F is F of G composed with F of F. This allows us to generalize a generalized probabilistic theory into a category. Our objects will simply be the systems A, B, C, and so on. Our morphisms will then be transformations between systems. We also want to have an empty system I. This can be interpreted as a system with nothing in it. This allows us to define states as transformations from the empty system to our system A. So a state on A is a map from I to A. This is interpreted as physically what is the information needed to prepare the system A into that given state. Dually, what is an effect in this category? We have effects correspond to morphisms from A to the empty system I. So this corresponds to the observed effect when you take a measurement. And lastly, what are probabilities or scalars in this category? They correspond to transformations from I to I. How is this viewed? If we have an effect from A to empty system I, and we are in state omega, which is a map from I to A, then the probability is A composed with omega, which becomes a map from I to I. So that's not the complete definition of a generalized probabilistic theory, because we still don't have the properties that the effects form an effect algebra and the states form a convex set, and our probabilities or scalars are an effect algebra or something slightly stronger. To impose these conditions, we need further properties in category theory. Namely, we need the coproduct of two categories. So what is a coproduct of two objects in a category? It's an object which we denote x1 plus x2, morphisms from x1 into x1 plus x2 denoted iota 1, and x2 into x1 plus x2 denoted iota 2, satisfying the following universal property. if we have any two maps, F1 from X1 to any object Y, and F2 from X2 to any object Y, there's a unique map F from X1 plus X2 to Y, such that F composed with iota 1 is F1, and F composed with iota 2 is F2, and F is the unique such map with this property. So that's a bit abstract, and it's defined in terms of that universal property. However, to understand this better, we look at what happens in the case of sets. So the category of sets is obtained as the actual sets forming the objects of our category, and the usual functions between sets being morphisms or arrows in our category. What would the co-product of two sets look like in the category of sets? It would actually be x1 plus x2 is the disjoint union of x1 plus x2, which can be written in the following way. Ordered pairs A star, where A is an x1, union star B, where B is an x2. Then the maps iota 1 and iota 2, which you can think of as embedding x1 into the coproduct and x2 into the coproduct respectively, become mapping A in x1 to A star and B in x2 to star B. And what would this map F be in terms of the maps F1 and F2? We have F of A star is F1 of A, and F of star B is F2 of B. And you can easily show that this satisfies the universal property of a coproduct. We also need the notion of a pullback in category theory, where if we have two morphisms X to Z and G from Y to Z, so these two maps on the right and bottom of the square here, what is the pullback of these two maps? It's going to be an object P with maps P1 and P2, P1 from P to X and P2 from P to Y, such that G composed with P2 is F composed with P1. So this is what we call a commutative square, such that it satisfies the universal property that any other object Q with maps Q1 to X and Q2 to Y, such that it makes the diagram commute in the following way, that G composed with Q2 is F composed with Q1. We must then have a unique map U from Q to P, such that P2 composed with U is Q2 and P1 composed with U is Q1. Again, this is a bit abstract as it's defined using the universal property. So let's look at what happens in terms of sets. So if we go back to this diagram and think of Y to Z and X to Z as functions between sets X, Y, and Z, what would this object P be, and what would the maps P1 and P2 be? The object P would be ordered pairs X, Y, where X comes from X and Y comes from Y, such that F of X is G of Y. P1 would then map the ordered pair X, Y to X, and P2 would map the ordered pair X, Y to Y. Let's see how it satisfies the given universal property. If we have other maps Q1 from Q to X and Q2 from Q to Y, what would this map U be? The unique map U, it would map any element Q in the set Q to F of Q, G of Q. Why would this be in P? It's because we assume G composed with Q2 is F composed with Q1. That means that F composed with Q1 of small q is G composed with Q2 of small q. So sorry, this F and G should be Q1 and G should be replaced with Q2. That's another typo. So F should be Q1 of small q, and the G should be replaced with Q2. And we see that G composed with Q2 is F composed with Q1. So that ordered pair should be in P. Lastly, we need initial and terminal objects in our category. An initial object in a category C is simply an object which we denote 0. However, you could represent it by anything such that for any object X, there's a unique map from the given object to X itself. For sets, what is this initial object? It's simply the empty set, because we know for any set X, they use a unique map from empty set to X. Dually, what is a terminal object? A terminal object in our category is an object, which I denote I, such that for any object X in our category, they use a unique map from X to this terminal object I. So what is this in sets? In sets, the terminal object is given by the singleton or a one-element set. And what is the unique function between sets from any set X to the singleton set? You simply map every element X in X to the element star here. Now notice I said the terminal object and the initial object, because it turns out that these initial and terminal objects are unique up to isomorphism in our category. So they become equivalent, so we can talk of a single terminal object and a single initial object respectively. So with these notions in mind, we can then define an effectus. So an effectus is a category C with finite coproducts, where we have this denoted as 0 plus. So 0 is our initial object and plus is our coproduct operation. Moreover, we have a terminal object I such that the following conditions hold. We have these two commutative diagrams in our category where these square brackets represent the morphism obtained by the universal property of coproducts. So we can have these commutative diagrams in our category. It holds for any category with coproducts, but here condition 1 requires these two diagrams to be pullbacks. So precisely the pullback that I mentioned. The second condition of an effectus is we want the following two maps, V and W, going from I coproduct I to I coproduct I, defined in the following ways. So like I said, these maps with square brackets simply come from the coproduct, the universal property of coproducts. We want these two maps to be jointly monic. What does this mean? If I have two maps F and G, whose codomain is the same as the domain of V and W, and we have V composed with F is V composed with G, and W composed with F is W composed with G, then this must force F to be equal to G. And these are the only two conditions needed to define what we call an effectus. So what are the properties of an effectus? These are precisely the properties that we wanted. Our transformations become partial maps. So this is a slight difference now, where instead of maps from X to Y, we have partial maps from X to Y coproduct, the terminal object I. What can we think of this as? We can think of this as partial functions. So if we think of sets again, Y coproduct terminal object will be the disjoint union of Y and a singleton set. And our function X will then map some subset of X to Y, and the remaining portion gets mapped to the singleton star. So this map is precisely what we call a partial function between sets. Again, our states are maps from the terminal object I to X. And now our effects are not maps from X to I, it's X to I coproduct I. Our scalars then become maps from the terminal object I to I coproduct I, and we get precisely the properties that we wanted. The set of states of a system form an abstract convex set, and the set of effects of a system form an effect algebra. Just briefly, how is the product of the effect algebra obtained from the definition? So suppose we have two effects given by A1 and A2, we can apply the effect algebra product on them when they are compatible. This happens precisely when there exists a map from A to I coproduct I such that V composed with A is A1 and W composed with A is A2, where V and W come from the maps in the definition of an effectus. In this case, what is the actual product, A1 product A2 in the effect algebra? It is this map here, where this is the codiagonal identity obtained by the universal property of coproducts composed with A. So this is what the product of the two effects actually turns out to be. Next, our product in an effectus is actually represented by a coproduct. However, the key difference here is that the coproduct of two systems gives us disjoint union of systems. This is a key difference from the Hilbert space formalism, as well as the formalism of quantum mechanics in a GPT, because we saw for the example of sets that the coproduct represents disjoint union. So a similar phenomenon happens here. What are some examples of an effectus? Any generalized probabilistic theory, any set, and more generally, any topos. And the opposite category of von Neumann algebras. Again, this is important as there has been work on quantum mechanics using von Neumann algebras. One more example that I don't have listed here is any extensive category, which is a useful notion studied in category theory. So what is the benefit of studying quantum mechanics using an effectus? It turns out, using an effectus, we get two notions of the comprehension of an effect and the filter of an effect, respectively, coming out naturally from the categorical structure of an effectus. These are sometimes also known as comprehension and quotients of your effect. Formally, what is a comprehension of an effect A, given at the top here? It's a map from SA to A such that A composed of this map, which I denote iota A, is 1 composed with iota A. What is this 1 here? It's the 1 of the effect algebra, which we can think of as truth. The 0 in the effect algebra would then correspond to falsity. Such that any other map U from U to A with the same property, that A composed with U is truth composed with U, must factorize through iota A through this map U prime for a unique map U prime here. And dually, we have the notion of a filter. So a filter of this map, of the effect A, is a map from A to this object here, or this system, which I denote Q subscript A, such that truth composed with this map is less than equal to the negation of A. Here, less than equal to is the same order that I defined on an effectus, such that any other map V with this property must factorize through pi A uniquely through a map V prime. So these are quite abstract. Concepts for an effect. However, they do have physical motivation. So a comprehension of this effect can be thought of as simply the largest subsystem SA of your system A, where the effect A is true. And dually, a filter of your effect simply removes all elements of your system where the effect A is true. So these are dual to each other. You have the largest subsystem where A is true, and for filtering, we want to remove all the elements where the effect A is true. And we call a map pure if it can be written as a filter composed with a comprehension map, where they are not necessarily associated to the same effect. And for quantum mechanics interpreted as a generalized probabilistic theory, these pure maps are in fact Krauss rank 1 operators, which is in fact a notion coming out of quantum mechanics already. Another important property of an effectus, from an effectus, we get a natural functor from the category of predicates on the effectus to the effectus itself. What is this category of predicates of our effectus? It's going to be the category where all the objects are all morphisms A2 should be I plus I. This is the category of all effects in our effectus. And morphisms in our category will then be represented by certain commutative squares, which I'm not going to get into too much. But what does this functor do? It takes an effect small a from A to I and assigns to it the object A in our category C. So why is this important? This forms an example of a functor, but why is this important? If we look at the fiber of a functor at an object X, this is a notion in category theory. What is it? It's a subcategory of your domain category where the objects are precisely those that are mapped to X and the morphisms are those that are mapped to the identity on X. If we look at the specific functor here, what is the fiber at any object X? It's going to be all effects on the object X, or all effects on the system X. So the fiber is in fact an effect algebra. This leads us to the notion of a form. A form in category theory is a faithful amnestic functor. So this is a particular type of functor in category theory, and it has the special property that the fiber at any object is a partially ordered set. Now recall that I said an effectus naturally forms a partially ordered set. So in this functor, which I call the form of predicates, it forms precisely a faithful amnestic functor up to equivalence. So it's an example of a form. And lastly, this form of predicates in certain types of effectuses where any effect has comprehension and quotient and so on, closely resembles what we call a Noetherian form. So a Noetherian form is a particular categorical generalization of group theory. So it holds for any group-like structure, so any algebraic structure with an underlying group-like structure, and it's self-dual, meaning that we can prove any result in this context proves a dual result, which we get by simply reversing all arrows. And the table above gives us some corresponding notions of a Noetherian form and an effectus. So for a general form, a sub-object is an element of the poset fiber. For a Noetherian form, we usually use the language of group theory. So in a Noetherian form, our sub-object is represented by subgroup. And for an effectus, our sub-objects are precisely the predicate from X to I, or all effects from X to I. For a form, we can also define what's known as left universalizer and right universalizers. And for a Noetherian form, these become embedding of conormal subgroups and projection of normal subgroups. For an effectus, this exactly corresponds to comprehension of a sharp effect and quotient of an effect, respectively. Where a conormal subobject is a conormal subgroup for a Noetherian form, and for an effectus, it becomes what's called a sharp effect. Lastly, this notion of a pure map, which is a comprehension composed of a filter, precisely corresponds to the embedding projection factorization for maps between groups or any map in a Noetherian form. More generally, this can be seen as the epimonofactorization in any variety of universal algebras. And lastly, below we have a chain of 5 adjoint functors, where the top one is for the case of an abelian category or abelian groups, where the 0 and 1 assigned to each abelian group or each object in an abelian category, the smallest subgroup and the largest subgroup respectively. This map on the left, or this functor on the left, assigns the quotient group for a given subgroup, and the map on the right corresponds to assigning the actual group itself. So that's what happens for abelian groups. For an effectus with both quotients and comprehensions of all effects, we get precisely a chain of 5 adjoint functors which resemble this very closely. So at the top, we have our predicates on the effectus. The 0 and 1 represent our falsity and truth effects respectively. This middle functor here is our form of predicates. And here we assign the object, which is the codomain of the quotient, or also known as a filter. And here we assign the domain of a comprehension map to a given effect. And then just to end off, what are some future research problems on an effectus? So as shown, an effectus naturally yields a form. The question is, can we classify an effectuses using this form? So what conditions can we impose on a form to ensure that the codomain is an effectus? Another interesting problem would be to determine all the results that are common to both Noetherian forms and effectuses. And lastly, this is something that, at least to my brief knowledge, I do not think has been looked at in detail. Can we study time in evolution in a generalized probabilistic theory, or more generally in an effectus? So would it be possible to define some type of Schrödinger equation or an analog of the Schrödinger equation in a GPT or an effectus? And lastly, just some references. So the top 2 references on effectuses, they were introduced by, I'm not sure if I'm pronouncing this right, but Bart Jacobs and his PhD student Cho, as well as other collaborators. And a lot of the information in this talk was in fact taken from these 2 sources. The last 2 references are on forms and Noetherian forms. Forms were introduced in a previous paper by generalizes, and it was developed in subsequent papers, as well as the thesis of Thomas Weichel. And the concept of a Noetherian form was introduced in the paper Duality in Non-Abelian Algebra 4. So this is where I'll stop. Thank you.
Yeah, thank you very much, Kishan, for the nice talk. And let's open it up for questions. And please, this is set up as a meeting, so please just unmute yourself and ask questions. Any questions here?
Maybe I have one, like a very naive question, just because this is all very new to me. But could you just explain, like, I don't know, maybe a bit of a high level, the diagram that you had, one of the last diagrams, I think it's on your like 3rd to last slide. Okay, we can see 2 slides now.
Sorry, I messed up the Zoom. Where did it go? Where did the Zoom go? Sorry, let's see if we can find it.
But yeah, my question is basically like, if you read a paper and you saw a diagram like that, would you immediately be able to like interpret kind of everything that they were talking about? Like, is there a specific way that you read the diagram or do you have to have like additional information?
So just to get the diagram you're talking about, are you talking about the chain of 5 adjoint functors?
Yeah.
Okay, so for this, for the category of abelian groups, it's known, but I'm not sure what your question is. When you see another paper and you see 5 adjoint functors, would it?
Yeah, like, I mean, just for example, like that top diagram, like, does that contain sort of all the information that you need to understand like some key concept of what they're explaining? I mean, I just,
Okay.
from my experience with the ZX calculus, you know, you can sort of everything that you need to know about the circuit is like in the diagram. Is something similar
Okay.
going on here? Like,
Yeah, so most of the information needed to study the generalization of say abelian groups or abelian categories is encoded in this diagram. However, there's still 1 or 2 extra conditions that you need to impose on these functors
okay,
so that it's like a complete
okay.
definition. But yes, so a lot of the information of studying abelian groups or abelian categories is represented by the functors in this chain, as well as the fact that these functors are adjoint. This is a special property in category theory.
Okay, so there's like a special way if you were more experienced with these diagrams where you can sort of read this.
Yeah, so in general, adjoint functors, the nicest example is free forgetful functors. So if you think of groups have an underlying set structure. So you have a forgetful functor from groups to set. So you take a group and you send it to its underlying set.
Okay.
And you have a functor in the other direction from sets to groups. Take a set and assign to it its free group on the set. This is a construction in group theory,
Okay.
but this forms an adjunction.
And then Kishan, Amy mentioned the magic word ZX calculus, which
Okay.
all we know coming from physics. What can we learn from this for those kind of applications? Oh,
I'm not sure about that at all.
okay. And another stupid question. One generalization of probability theory, I think for non-commuting kind of observables, is free probability theory. Does that fall into your generalized probability theories or not?
So yes, they generalized probabilistic theories do can be used to study probabilistic examples as well.
Mm-hmm.
So I don't know too much about those details, but I know it's not just for quantum mechanics, as well as an Effectus. I didn't include some of the other examples, but there are actually probabilistic examples as well. So there's something called the Clausius category of the distribution monad, which is classically studied for probability theory. So it has a strong connection there.
Mm-hmm. Okay. Thank you. Are there questions from our online participants? Please just unmute yourself and ask. And maybe while they think, you mentioned that there is no kind of Schrödinger equation in this general setting. What would you expect it to be?
So my naive approach, I'm not sure if this would work at all.
Yeah, I don't know.
But you'd have to parameterize the state on time, right? So that would be our evolution of state depending on time. Now, in a categorical setting, this would be something from, say, the category of non-negative reals to the set of states of your given system, which should form a functor. And then what extra conditions do you need to study time evolution more? So I'm not sure what other details are needed, but some sort of functor like this might.
Okay, that would be very interesting to see.
So it's like you're going from time, like your arrow takes you from time to the state at that time.
Yeah.
Okay, that's
Precisely.
interesting.
Yeah.
But so on that point about time evolution, so for the GPT, you don't have a notion of time evolution there.
So to be honest, I've only looked at a couple of papers on GPT, and I did try and search for time evolution in a GPT, but I didn't
Okay.
seem to find any.
Because on like quite early on in your talk on the slides, you had a slide where you listed how to compute like probabilities using
Yeah.
effect, and that to me looked very much like a POVM formalism,
Yeah.
like a positive operator value measure.
Okay.
And to my knowledge, you can represent POVMs can be represented in terms of completely positive maps. So you can describe the action of measurement in terms of completely positive maps, but you can also incorporate time evolution into that. So time evolution are just completely positive maps, which are a one parameter variety of completely positive maps. So they depend on some parameter t, which is time basically. So I don't know if there's some kind of.
Okay, so maybe it exists, but if not, maybe we should actually look into that.
Yeah. Okay. I'm not sure about the effect because it was on your slide about the GPT, so I don't know about the Effectus or anything else
Okay.
about that. But
Sure.
Okay, a few things to explore. Any more questions? Okay, the online audience is quiet. so let's thank Kishan again. Kishan. Oh, sorry. No, this is just people clapping.
Oh, okay. Okay.
This is online clapping.
Okay.
So thank you very much, Kishan. We can clap for real here.
Thank you.
Thank you very much. And please keep us updated on what happens because there seems to be lots of interest. Yeah?
Okay.
Thank you very much. Thank you. Thank you very much to the online people. Have a good weekend. Thank you. Bye. Bye.